Good to go? Awesome. Can everyone hear me all right? Great. Thank you all for coming to an introduction to IoT hacking. Just a quick introduction about myself before we get started. My name's Aaron Wasserman. I'm a senior security engineer at an offensive security firm called Praetorian, where I'm a member of the IoT team. I have my master's in electrical and computer engineering from Georgia Tech. That's where I fell in love with hardware hacking. I've got my whole alphabet soup of certifications here, but the one that might be relevant to this talk is the Attify Certified IoT Pentester. I'll try to talk about that a little bit at the end to see if it might be a good fit for anyone in the audience who's interested. And please do connect with me. My website is just myname.com. It's got a link to my LinkedIn and new Twitter account. It's a little bit dry at the moment, so please forgive me. I'll have some cool content on there soon in the future. And then just one more quick plug. If anyone is looking for a new role in offensive security, Praetorian is hiring for a lot of open roles right now, not just in IoT, but across disciplines. So if anyone checks out those roles and they're interesting, please feel free to stop by the IoT playground, and I'm always happy to chat about it. But now on to the talk. So this talk kind of serves to address a gap that I found when I was trying to learn about IoT hacking, which is that a lot of the talks did a great job of picking kind of a subset of topics and exploring them very thoroughly, but none of them really gave the 10,000-foot overview of what are all the subtopics. So in this talk, we're going to start by establishing a methodology for performing IoT hacking. Then we're going to try to speed run at a very high level, lots of common techniques and tools that you might encounter. This is going to be fast, but if you have any questions, again, come by the IoT playground. We've got lots of these tools and some vulnerable demos that you can get hands-on with. And unfortunately, I am going to have to cut this voltage fault injection to make time here, but we do have the hardware again at the playground, so if you're interested in that, we can chat afterwards. So starting with the methodology, I think one of the pitfalls that people can run into when they start working with hardware hacking is that's all they focus on. It's all the flashy new stuff that they're learning for the first time, and they forget, the basics. And really, you can't just go straight to the hardware and call it a day. You have to make sure that you are still being very methodical and procedural. So that starts with a system walkthrough and recon. I'll talk a little bit about what that entails. I think a threat modeling process is a really valuable part of any security assessment, even if you may not be required to perform one. Active testing is going to vary a ton based on what devices you're actually testing. Right, you can't do Bluetooth hacking on a device with no Bluetooth, so this varies pretty heavily, but we'll talk about it a lot of the common themes you may see. And then if this is work for a client, right, what goes into reporting and debrief? Are there any special considerations? And do they need retesting for this, which can be a challenge in the IoT space? So for that system and device walkthrough and reconnaissance, the first step is understanding the device as a normal user. If I'm testing a medical device that I've never used before, right, how am I supposed to find vulnerabilities in something that I can barely operate? So the first step is to read the user manual, read the documentation, and familiarize yourself with the normal business use cases of the product. And start to understand what external interfaces does it have? Does it have USB ports? Does it have an Ethernet jack? Start to think about what attack surface you might be able to exploit. Does it have wireless interfaces? We'll talk about lots of options for that in the future. And since it's hardware, crack it open. Right? First, of course, make sure if you're working with a client that destructive testing is in scope. Sometimes they need it to come back functional, so you should, of course, be careful and respect that. You should also see if they can send you multiple devices up front. There's a good chance that you break one doing some of this destructive action, so you want to make sure that if you do break a device during testing, you have a backup. Check for any interesting headers on the board, anything that looks out of the ordinary, and research if other people have seen this before. A lot of times you may be able to piggyback off of other people's research or vulnerabilities in subcomponents. So, supply chain is always a hot topic. And now I mentioned the threat modeling a little bit earlier. So threat modeling helps assess the risks and consequences that a product faces. This is really helpful at all stages of a product development lifecycle, but I'm really focusing on it through the lens of security testing. And one of the great things that this can do is it can really be helpful in targeting your testing efforts. So a lot of times on a time-boxed short engagement, you might not be able to explore everything thoroughly, but if you can understand where the high-value assets in the system are, you can look at tasks and attack paths that prioritize reaching those assets. It also helps you ensure appropriate coverage of the whole system. Right, if you have a novel technique you just learned with your fancy new tool, it's very easy to focus on that directly and leave out some low-hanging fruit that could have very critical real-world consequences. Right, as IoT makes its way into medical devices, cars, right, the risk of a security vulnerability goes from privacy violations and stolen credit card details, which are already bad, to potentially life-threatening problems for a patient using one of these devices. So you really have to make sure that you're covering the system appropriately. And it also forces you to look through the lens of an attacker, right? When we were doing that manual walkthrough, we're figuring out how the system is supposed to be used. But attackers don't use systems the way they're supposed to be used. They abuse and they exploit them. So by going through this exercise, it kind of forces you into that mindset. I have a couple blog posts linked at the bottom here from the Praetorian blog talking about our threat modeling process. Again, it's very similar to what I've been discussing here. We want to focus on finding the critical assets, right? So for a medical device that takes readings, right, it may be the integrity of those readings. It could be very bad if you can manipulate a device to return twice the value, right? That may impact how much medicine someone administers, right? So understand the critical assets. What are the crown jewels of the system? What keeps the manufacturer up at night? If they get that call at 2 in the morning that, hey, the product's been hacked, what's the first thing that comes into their head as, man, I hope they didn't get that, or I hope they can't do that. The next thing you have to figure out kind of user roles and privileges. In some applications, like if you think of a normal web application, this may be very easy. There may be, a standard user, someone who has edit permissions, someone who's the owner. But with the hardware realm, there's another paradigm, which is how much access do they have? Is it someone who has physical unattended access to the device for multiple days or overnight? Is it someone who's, 30 feet away or 15 feet away but never has the device directly? Or is it an attacker over the internet? So understanding, what attackers you're modeling for can help inform some of your paths. The next thing is figuring out the attacker terminal goals. This usually relates back to those critical assets very well, right? The attacker wants to compromise personal health information as their terminal goal, or they want to cause violations of integrity for medical device measurements. The attack surface is all of those things we were finding during our walkthrough, the exposed external interfaces, wireless interfaces, any way that we can attack the device. And finally, the attack paths map the attack surface to the critical asset. So an attacker will utilize unauthenticated Bluetooth requests to compromise personal health information. So that's what an attack path might look like. Now we move into the active testing. Again, I'll go through kind of lots of tools and techniques in a little speed run section here in a little bit. But some of the general categories you'll see, first of all, hardware, right? The T in IoT stands for things. There is some tangible device that we're working with. So are there debug pins that the developers left enabled unintentionally or intentionally? Can we extract data from the memory, right? A lot of times when you're doing web app assessments, it may be black box. But if you have the physical device and you can extract the memory, well, suddenly you may have source code from the file system. You may have a binary you can reverse engineer. You can start to get lots of information. And you can also sniff data buses. If things are being encrypted at rest and being encrypted in transit to the cloud, but not being encrypted in transit between 2 chips on the same board, you may be able to sniff for sensitive secrets that way as well. For wireless and network interfaces, lots of your foundational encryption, authentication faults, the ability to man in the middle of the connection is also very important here. Firmware analysis. If we can get firmware off of the device, this could look like a number of different things. Some IoT devices will just have bare metal firmware that you'll have to go right into a disassembler, decompiler, and start picking it apart. Some will have a full Linux file system, and you may be able to just walk through the directory tree like you've done 1,000 times. And again, checking out in the firmware, how does it handle updates, right? If it's getting these updates from the cloud, is it validating those certificates? Do they have shared secrets? Are those secrets a fleet key, right? Could we find a secret hidden in one device and use it to exploit thousands over the internet? And then finally, cloud communication. A lot of these will use the cloud for over-the-air updates or sending analytics data, getting patches, all kinds of different stuff. So taking a look at if the cloud infrastructure itself is secure, and then taking a look at the communications to and from the cloud. And then again, when it comes to the reporting, I think it's really important to communicate the impact. Right, if you've seen a cross-site scripting attack and you get, your alert XSS box, you might understand the implications of that, but maybe a less technical stakeholder doesn't really understand how that can be used to target it. And very similarly, once you get onto, pictures and microscope pictures under a PCB, people might not understand the impact of what they're seeing. So really making sure you express the real-world impact and try to tailor it to the customer's needs, right? If they're a medical device and they're submitting for, FDA compliance, they might have some very specific requirements about what's in the report, how it's structured, maybe some details you wouldn't really extrapolate on usually could be very important here. And retesting can also be a challenge because for a lot of these devices, they might be deployed in the field and not have an over-the-air update mechanism. So for some of these devices, a firmware update might be a technician going to the field to update it. Or if it's a hardware vulnerability, there may be no fix they can do in the field, and it's just permanently vulnerable until a new generation comes out. So now this is going to be the fun speedrun section. There's great resources for basically all of these online. So my goal is to tell you what's out there and maybe where you can look to learn more. Again, for a lot of these tools and techniques I'm talking about, we have practical examples you can do hands-on today over at the IoT Playground. So do consider stopping by. I see a lot of faces that we've seen already, so lots of fun to be had. I also want to call out this VoidStar link at the bottom. This is a really great discussion for setting up your home lab. What tools do you need? What's most important? And offering some good recommendations at different price points. So for a lot of the items I'm going to call out here, I'm leaving prices off of them, and I've just got lots of fun pictures. But if you do want to see a price breakdown and feature comparison, that's a great resource to go look at. So starting off with basic tools and equipment, these are going to be useful anytime you're working with hardware, no matter what the device is. These are going to come up time and time again. So your hand tools are going to be a good place to start. The nippers in the top left, also called flush cutters, diagonal cutters, a million and one names. Those are going to be your best friend. And honestly, for some finer gauge wires, you'll just end up using those as a wire stripper. You won't even bother grabbing wire stripper half the time for them. So getting a nice pair of nippers is really great. Below that, from the same color scheme, there's a set of pliers. These ones are really nice. They have no serrations on the inside, so you're not going to mar up the surfaces you're working on. And they've got a nice curved radius on the outside if you want to put a bend in a wire, so that can be helpful as well. For a wire stripper, you can get really whatever's comfortable for you. There's some that are kind of spring-loaded where you squeeze them and they bite on the wire. There's kind of standard ones you'll see like this. I think one of the big things to watch out for is make sure you get ones that go up to pretty thin wire gauges. So this goes up to 30. One you might see at like a hardware store for an electrician, they'll be using a little bit thicker wires that we just don't need for a lot of cases. And finally, a nice set of tweezers will go a long way. I like to have straight ones with a curve. And these reverse grip ones all the way to the right are really great. They'll constantly apply tension, so it's always holding the part until you choose to let it go. So if you're dealing with really small parts under the microscope, that can be a really nice hand. Next, we got to figure out how we're actually making some of these connections. So over on the left, there's some male-to-male, male-to-female, and female-to-female jumper wires. I like to treat these like they're disposable. I don't think any of them on the market are really great. You'll always have some where the electrical connectivity isn't perfect, and you'll spend a couple hours troubleshooting it, and you'll curse them and throw them in the trash. But at the end of the day, if there's no good option, just treat them like they're disposable. At the top in the middle, that's a solderless breadboard. So those have little strips of metal on the inside that the wires can friction fit into. So you don't have to solder all these wires together. You can use that for kind of temporary prototyping connections. You may also encounter cases where you have to make like a voltage level translator, and just prototyping one on one of these little breadboards is very handy. Then below that, there's some male and female pin headers. Sometimes if you open a device, you'll see the footprint or the holes and pads on the board for a header, but they didn't populate it, so they didn't actually put the part in. So by having these headers available in a little kit of lots of different sizes, that can help you hooking up to these devices. And then finally, if the jumper wires aren't doing it, you need some really thin wires for particular applications. If you search for wire wrapping wire, that's a really good source for getting a lot of these thin wire very cheaply. And then there's also this enameled magnet wire. A little bit harder stripping that enamel coating off of it. You can use sandpaper. You can try to burn it off with the tip of your soldering iron, or scrape it with an X-Acto knife. Lots of different approaches, but that can come in handy as well. But I'd say the jumper wires you're seeing a lot more often. So I mentioned some soldering there with the wires. Next up, you're going to want some sort of soldering station. If you go check out the Hardware Hacking Village, I know they have some soldering stations ready with some kits that you can be making here today. So again, go get your hands dirty, try it out. With the soldering stations, you can get some pretty cheap ones that will serve you pretty well. But if you're looking to get a somewhat more serious upgrade, the big thing you're looking for is adjustable temperature control. So I have this light teal Weller WES51. I think they've discontinued it and replaced it with like a WE2020, but that's a great option. The dark blue one at the bottom is the Hako FX888, very popular one that'll also serve you well for most applications. In the top right is a hot air rework station. So I have the picture of two different packages, an SOP and a BGA. You'll notice the SOP has pins on the side of the chip that you can get to with a soldering iron. But for the BGA, instead of having pins, it has a bunch of solder balls on the bottom of the chip, and you can't get an iron down there. So you have to use something like a hot air station to heat up the whole surface uniformly until those will melt. So you can get a nice cheap one. This 858D, there's a million reskins of it on Amazon, AliExpress, eBay, wherever you like to do your cheap component shopping, and all of them work pretty well. Soldering extras. For solder, I like to get a couple different thicknesses. So I like to have a thicker one for through-hole parts where I'm putting down more solder and just want to get it down quickly. But then also having a thinner diameter so you get a little bit finer control over how much solder you're dispensing at once for some of those smaller surface mount parts. Now with soldering, you're always going to put solder where you don't want it. So that's where the solder wick and then below it the silver and blue tool called the solder sucker come in. With the solder wick, it's just a twisted copper braid, so you can place it over the solder you're trying to remove, hold the tip of your iron on it, and as the solder melts, it'll get soaked up into the wick, and you can remove it. With the solder sucker, there's a plunger that you depress, and it holds into place. You hold the tip of it up to the solder you're trying to remove, melt it with the iron, and when you press the button, the plunger's released, and that vacuum force, hopefully, it removes the solder. Sometimes it takes a couple tries. It can also be helpful to get a couple different tips for your iron, experiment, see which ones you like, see which ones you can get good thermal contact with. I like the ones that are kind of shaped like a rounded off flathead screwdriver. I find that I can usually get pretty good results with those, but sometimes you want a really fine cone like the one all the way to the right. That can help with some of the really fine, tiny pins. And the bottom left is flux. Flux is really going to help through the soldering process. I'm not sure if they have flux over in the Hardware Hacking Village, but if they do, check it out. You'll get a very good idea why it's helpful very quickly. This brass blob in the little silver container is for cleaning the tip of your soldering iron. So you can just run the tip through this abrasive brass, and it'll help keep it clean as you're working. This tape is a type of tape, I think the kind of brand name is Kapton tape, but it's very thermally resistive. So if you have areas that you're trying not to burn or trying not to have desoldered, Kapton tape can help to mask off those areas so you don't hit components you're not trying to. Even if you're using unleaded solder, you're still making molten metal, and the fumes are not something you want to be breathing. So I have to put the fume extractor on here just to feel good about it. But a lot of times I will not bother pulling it out if it's just a small soldering job. If I'm going for a couple hours trying to mass produce something, yeah, I'll pull it out. But otherwise, you're in control of how concerned you are about your health. But remember, you are melting metal, and there are fumes that you probably do not want to be breathing. Then finally, in the bottom right, or I guess second to finally in the bottom right, is some solder paste. When you're working with those surface mount components, you really might want to avoid using the iron for some of those surface mount components. So with the solder paste, you can put daubs of the solder paste on all the pads you're trying to solder, put the chip or component you're soldering kind of into those globs of paste, and then use the hot air rework station to melt them all down, and it'll kind of shift its way into place. And then finally, these Otis brushes, they're like officially gun cleaning brushes, but I saw someone recommend them on Twitter for cleaning flux off of circuit boards, and they work really well with some isopropyl alcohol, so wanted to throw those in here. A multimeter is going to be one of the most pivotal pieces of equipment in your toolkit. As the multi might suggest, it can do all types of different measurements, voltage, current, resistance, but the things you're going to be using the most are checking the voltages of different signals, different pads, and then also doing continuity testing. So a lot of these meters will have a mode where if you touch the two leads together, it'll either display something on the screen or it'll make an audible beeping noise. So if you're trying to figure out where one pin is connected to, you can hold one lead on that pin and probe around to all of the test pads or other pins or components, and when you hear a beep, you know that's where a connection is. I also recommend getting a set of leads, having some finer point tips, some alligator tips, and some retractable spring-loaded clips can be really helpful for different circumstances. Next up is a power supply. Sometimes we're going to have to power things not how the original product is set up. If we have to remove a component from the board and power it externally, something like this comes in handy. The cheaper ones on the left, again, there are tons of reskins of them. They all do about the same thing and work pretty well and will serve you for a lot of your use cases. This is also a great DIY project. If you want to get hands-on with hardware, you can take like an old ATX computer power supply and make your own variable power supply, or have a couple different voltage output levels based on what you typically use. One benefit of going up to a more expensive unit, like the one on the right, is that they can offer remote control or programmable features. So some of them will have an API that you could hook up to, say, a Python script. So if you're trying to do some automated testing, that feature might be important to you. Holding and probing. We only have two hands, and if you have one held up with solder and one held up with your soldering iron, you're out of hands. So having some different solutions to help hold different items and hold wires down, make connections, can be really helpful. The stick vise on the left I really like because it's so flat and low profile. I'll talk about magnification a little bit, but this one's great to have under a microscope because it's not eating up a ton of the available height that you have. You might have also seen helping hands where it's like two metal arms and a magnifying glass. I think those fall apart pretty quickly, and 2 arms is just not enough. So I like ones like this yellow one with 4 arms. I have some with 6. Kind of just look around, see what you like, but I'd steer you away from those, 2-arm metal with a magnifying glass helping hands. These were life changers for me when I got these. On the left is a PC Byte kit from SensePeak. It's a metal plate on the bottom, and then it has little standoffs that can hold your board. It's insulated, and then it's little adjustable arms. So they have a magnet in the base, so they hold down onto the plate, and you can position them, and they have a pogo pin in the tip. So you can rest them on the pin or the test pad that you're trying to target, and then you have the leads off to plug into whatever equipment you're using. These are really great and can come in handy. A lot of times you might have had to solder something in the past. You can get away with using the SensePeak. To the right of that, these are sold under a number of different names. I found the best luck Googling for them under like SD card flash repair tool. They're a little bit more finicky to get those needles aligned properly, but once you have them, it's a little bit more permanent of a solution once you screw those screws down. You could pick that up, walk around with it. With the PC Byte kit, if you bump it too hard, those arms will start to fall over. So if you have something that you want to be probed for, a couple weeks, it may be worth the time playing around with that needle flash repair jig. Next up is Reconnaissance. So once we have a device, we need to start figuring out what's there, how to take it apart, and get into it. So a great screwdriver set is really essential here. You're going to run into all kinds of crazy bits. Make sure you have some nice security bits as well. I also recommend getting a little magnetic parts dish, or there's some like silicone desk mats with little pockets you can put screws in. That's really helpful for staying organized and not ending up like me, where you have tons of electronics that are missing a screw or two. They're mostly put back together, but they have some battle scars. You'll also want some spudgers, picks, pry tools. Guitar picks also work really well for this. I have a whole bucket of guitar picks, so I frequently just use those. But that'll help if you have any plastic clips or friction fit parts just to pop them open. A utility knife, like an X-Acto knife or any brand of your choosing, especially if you have a kit with some different shaped blades or maybe some different shaped handles for getting into different locations, that can be really helpful. And then sometimes the devices are really not made to be opened up and put back together. They'll have friction welded or heat staked components, and sometimes you'll have to drill those out. I have a picture here from an iFixit teardown guide on the AirTags where they are drilling it out. For the AirTag, you actually don't need to drill it out, but I thought this was a nice studio photo to include here. And then I mentioned a little bit earlier, magnification. My eyesight is not great, and some of these components are small. So having some solutions for magnification can be really helpful. Over on the cheaper end, they have these magnifying headsets. I think these are actually pretty good for doing like inspection after you've done a soldering job, but I find that if you're trying to solder while wearing them, it can be kind of awkward and they can get in the way. In the middle is a digital microscope. These are really cool as well. You can hook them up to your computer, a phone, a tablet, and get a live feed. But I think the biggest problem with these is that you lose your depth perception. So if you're trying to solder staring at the screen, it can be really hard to tell how high your iron is off the board. That said, they are really great for taking photos as you work for documentation or reporting purposes. If you're doing this a lot and you really want to make the investment, getting a stereo microscope is really fantastic. You keep your depth perception. It makes soldering small components really easy. And if you get one with a trinocular port, like the one shown on the right here, you can put a camera in that top tube. So again, for documentation or reporting purposes, you can get some nice professional zoomed in images so people can really see what's going on. Next thing we want to do is open up our device and start poking around. So we can use that multimeter in continuity mode, like we mentioned earlier, to start moving around, poking pads. If you're testing something open source, you can look at the schematics, board layouts, or maybe your client provided those to you. If it's something where you can't probe the pins directly, say it's one of those BGA packages with the solder balls on the bottom, you can get a sacrificial device, remove that chip, and probe from the balls underneath where the chip was to any test pads. So here we're looking for interesting chips, test pads, connectors. The top image is iFixit teardown of the AirTag. Over on the left side is an NRF52, that's the Bluetooth chip they're using. Below that is an external memory chip that has the firmware for the U1 chip, and that silver chip is Apple's U1 chip. Then the image on the bottom is following reverse engineering efforts from Colin O'Flynn of New AE Technologies. So he figured out what all of these little gold test pads on the board were mapped to, again, either by going around and tracing it with a multimeter, or there's some other methods as well. Also look up data sheets. Anytime you see a part number, go see what you can find online. A lot of these will have tons of information. So this particular data sheet you can see has 555 pages. It's that Bluetooth chip off the AirTag. Lots of information here. Luckily for us, we really don't need it all. We need to understand how it interfaces with the world, any pin mappings so we know how to hook up to it and talk to those interfaces, and then anything that's security-related controls like debug access lockouts, code readout protections, stuff like that. But otherwise, we really just need to know how to hook up to it and what there is even to hook up to. Another great resource is this fccid.io website. So for any products that have to comply with FCC regulations, you'll be able to search up their FCC ID and find them on here. You'll find internal and external photos. So this is a device I want to take a look at in the future. It's an external air management system for like automotive suspension. I have one in my car. And just from going on this FCC site, before I have one that I'm willing to tear apart, I can already start looking at the board layout here. You also may find test setup details, and if you're lucky, even a parts list or schematics, but a lot of these manufacturers will request that those be made private for IP reasons. This is where it really splits up based on what you're testing specifically. So again, you can't hack Bluetooth if your device doesn't have Bluetooth, or I guess that's in the network interfaces, but the same applies to hardware. So you have to know what's kind of in scope here. So one thing you're going to encounter a lot is these serial UART interfaces. So UART is Universal Asynchronous Receiver Transmitter. As you might be able to determine from the universal, these do not have one sole purpose. So sometimes you'll connect to a UART interface and you'll get a root shell. Awesome. That's in a lot of the intro to IoT hacking videos you might find on YouTube, where it's here, find the UART shell, or find the UART interface, connect to it, root shell, profit. But sometimes it's a custom interface for proprietary serial commands. Sometimes it's just a boot log. Sometimes it's really just startup information. So what you get varies, but certainly if you see something that looks like a UART interface, certainly worth taking a look at. There's this video from the Flashback team called A Hacker's Guide to UART Root Shells. Highly recommend it. They do a great job of breaking down the protocol, how it works, how you can talk to it, and identify it on the board. Just for a quick summary, since you'll see this one so much, since it's asynchronous, you'll have to specify the baud rate that you're communicating at. I've listed some of the standard ones and bolded the ones that you may encounter the most. But if you're seeing garbled data on the output, trying a couple different speeds may help that data come through. And then this is just showing how a particular frame of data is structured. Again, that video will explain it all very well. Or if you want to talk in more technical detail, again, stop by the IoT Playground. When we're looking for this on the board, we're typically looking for between 2 and 4 pins. So silkscreen is the term referring to all the labels on a printed circuit board. So if you see something labeled TX and RX, your alarm bells should be going off and you should take a look at that. But sometimes it's more than just 2 pins. They'll have the ground pin with it, or they might have the supply voltage pin as well. So that's why I say 2 to 4. You need at least the TX and RX, and you could find your own ground source on the board, but sometimes those will be bundled. So in this photo from a VoidStarSec blog post, there's it seems kind of dim here, but there's that 3-pin interface circled in a yellow box on top. That would be a pretty good target for a UART interface here. This also manifests itself in different ways. It's not always just a header or pads on a board. Sometimes you'll see like a stereo, auxiliary cable, like a headphone cable that all of our badges have for our fun trading here at this event. And also some more creative solutions. So on some of the old Nexus phones, the USB connector could actually be multiplexed to expose the serial interface. And there was a similar technology called earjack that Google had a patent for, where on the tip connection of a headphone jack, if you applied a certain voltage, it would cause the ring and sleeve pins to expose the serial interface as well. So some hidden ones is there as well. So if we don't have any labels and we're trying to identify the pin out ourselves, we can use our good old trusty multimeter, find out which one is ground and which one is power, and then do a 50-50 guess for the RX and TX. That doesn't work as well for some protocols that require more wires. Or we can use a logic analyzer or an oscilloscope. Logic analyzers are really great. These can help you see more than just a point-in-time measurement. So the multimeter will tell you the voltage right now. This will kind of show you the whole waveform and help you decode it. So varying price points, again, check out that VoidStarSec blog post. Really great breakdown of the feature differences and cost differences. But this is what you might see. So again, we have our RX and TX pins here, and we can see that there are pulses on these lines encoding that data. And with the logic analyzer, we're able to have that help us decode the information. So here it's saying machine model rock chip RK3128. So we're able to start seeing what's going across these buses, right? And depending on the design of the system, that could be pretty sensitive, or that could take inputs. Again, it's universal, so you're gonna have to get in there, play around and see what it does. But again, that Team Flashback video, really great introduction to this stuff. An oscilloscope is another tool that you're going to use to help you look at signals over time. I think if you had to pick between a logic analyzer and an oscilloscope, the logic analyzer is going to be a lot more useful. I think it's more niche cases where you'll have to pull out an oscilloscope. But some of them, like this Rigel unit on the right, are mixed signal oscilloscopes. So they actually do have some digital pins at the bottom and can perform a lot of these same functions, but sometimes you're paying up for it. So this Rigel on the left, the DS1054Z, people kind of call it the hacker's scope. That's a very popular one, and it should meet a lot of needs until you get into some more specialized testing. Again, VoidStarsec does a great breakdown. And if anyone is a fan of Dave from EEV blog, go watch all of his videos on oscilloscopes. You can have a fun weekend watching all of those. So now we know where the pins are. We know what they do. How do we talk to it? A number of different general purpose kind of multi-tools. The Bus Pirate in red here is one of my favorites. So you can use that with a utility like Screen or Minicom, configure it appropriately with the right baud rate, parity and stop bits, and get talking to it. There are also other general purpose tools like the Attify badge shown there in black or the Shikra. These will all do just about the same thing, so find one you like or one that's in your budget or one that's accessible to you and get hacking with it. Another thing you'll come across is debug interfaces. So what you'll see here frequently is JTAG and SWD. SWD is basically like a two-wire variant of JTAG, and I've got this whole crazy JTAG state machine here, but luckily for us, until you're doing some pretty specialized exploration, we don't really care how that works. We just care how do we hook up to it and how do we talk to it. And once we are talking to it, we can extract onboard memory, reflash it with maybe malicious firmware, and do active hardware debugging of any running program. So we can glean a lot of information from the systems this way. With JTAG, you're going to have those 5 mandatory pins. They're packaged all kinds of different ways. I have some of the standard form factors up on the slide here. Also in the bottom, that's called a Tag Connect connector. So that company is working to kind of create some standard debug cables where you can have one cable clips in. They all have the same footprint. So if you see any of these footprints, maybe it's worth it for you to grab one of those cables. For SWD, you only have the 2 pins you're looking for, again, plus maybe ground or some with it, but you're looking for the data and the clock lines. So like I mentioned, with the identifying the UART pinout, right, once we have the VCC and ground, we can just 50-50 guess for the RX and TX. But for the JTAG, where we've got these 5, that's going to be a lot harder. So that's where tools like the JTagulator or JTAG enum, which you can flash onto like an Arduino Nano, come in. The JTagulator, I think it might be discontinued, but I think you can still get your hands on them from some vendors. They're really great. The idea with both of these tools is you take all of the test pads that you think might be JTAG, plug them into the JTagulator or JTAG enum, and it will go through and it'll try to brute force and figure out what pins are mapped where, and it'll spit out the answers. It'll say, hey, the one you have into my IO17 pin, that's your clock pin or what be TDI, TDO. So really, really helpful tool, can save a lot of time if you don't have labels or those schematics. Now that we know what the pins do, we have to figure out how to talk to it, and that's where debuggers come in. In the middle is the Seger J-Link. That's kind of like one of the go-to ones, but unfortunately they are very expensive. But I will say you are kind of paying for what you get. On the box, they have the quote, "It just works," and it really does just work. There are cheaper options like the one on the left. You can get various clones of those on Amazon for $4. But you will have some headaches with specific chips that might not be supported or problems working with the open source OCD software. It's great for a lot of cases and it's awesome to get you started, but as you get more serious, you may want to get some more of the manufacturer specific debuggers. On the top right is the TI, Texas Instruments MSP FET. That's great if you're working with MSP 430 microcontrollers, so if you see those, that's a great option. And then at the bottom is the ST-Link, so working with STM32 processors, things like that. Some mitigations manufacturers can do to try to stop you from abusing these interfaces. Some chips allow you to blow a physical JTAG fuse that stops you from accessing it in the future. Some allow you to enable JTAG password protection, and some enable other forms of access port protection or code readout protection, but some of these are vulnerable to bypasses. Stop by the IoT playground, show you what we mean. Another thing we'll find is some external memory chips. So sometimes the microcontrollers will actually be storing their firmware in another chip or storing, otherwise potentially sensitive information. And these talk over a number of common protocols. One of those is the Serial Peripheral Interface, SPI or SPI. Again, we don't really need to understand all of the intricacies of how it's working so much as we need to know how to connect to it and what tools we can use. One great way to hook up to these pins is these little micro grabbers. As you press on them, two little arms come out the top, and when they retract, it squeezes down and grabs whatever pin or wire you're trying to hold on to. These can work really well, but then there's also some other options. On the right here, you can see one of these clips. If the chip you're trying to extract the memory from is a standard form factor, you may be able to purchase one of these clips that slots right on, saves you the time trying to solder or use those finicky little clips. Also, sometimes you do have to take the chip out of the board. One of the problems is as you try to power up the memory chip to try to read from it, that can also power up enough other systems on the board that start trying to read the flash, and then it's busy when we're trying to talk to it. So sometimes you do have to take the chip off the board, and something like a T48 programmer on the left here supports tons of chips. It's very fast, great option for working with a number of different memory formats. Once we have a binary dump off of the device, we need to figure out if we have anything useful. Binwalk is a great utility for trying to find structure in large sets of binary data. It can look for magic numbers and headers that it recognizes are associated with certain data formats, and it can try to extract those for us, and we can see what we get. So in this output at the bottom, we can see we have some compressed data, we have some U-boot version strings, so it may be using the U-boot bootloader. We see a squashfs file system at the bottom, so maybe we're lucky and that's a whole Linux file system we can go start poking around. Another protocol you're going to see a lot for extracting external memory devices is I2C or I2C, or if you meet a real old timer, they might call it IIC. So if you hear any of those, that's what this is referring to. With this, you're just going to have to find those SDA and SCL lines. And again, the same tools like the bus pirate, those will be very helpful for interfacing with that protocol. Another thing is looking at bus sniffing. So sometimes systems will have multiple chips on them. Maybe one handles the Bluetooth and one handles the normal operations. And if they're sending data unencrypted to each other, you may be able to sniff that data and obtain some secrets. So this photo is from a video from a researcher, Thomas Roth, or Stack Smashing. He's done some work against Lenovo laptops where he sniffs the BitLocker keys out of the TPM as they're being sent over to the processor. Really cool watch and demonstrates this concept very well. Bonus round, auto. I don't do a lot with automotive testing, but some of my coworkers are very passionate about it. You're going to get a whole mess of automotive protocols. CAN bus is one you're going to see a lot. And it helps to have some of these OBD2 adapters. This is the same thing they'll plug into your car when you're going for an emissions test. So using that port to check out the automotive networks. Now moving into what we have for wireless or network interfaces. So if it's just using Wi-Fi, does the device host its own wireless access point? You'll see a lot of times IoT devices will host their own setup network that you can connect to and then point it to your own Wi-Fi network or just do all the configuration you need there. So for that access point, if it exists, is encryption used? Does it have a fleet key? Is there a default password that you can use against any device? Are there backdoor passwords that will get you in even if the password's been changed? So that's good stuff to look into. Also, if the device connects to other wireless access points, does it inherently trust the network it's connected to? Does it look for a pre-configured network name? Sometimes you'll find conditions where it looks for the name of a network in the manufacturing facility, and if it finds it, it might do some different actions. So if you configure an AP with that same name, it might start acting differently. How is the key configured? And then finally, treat it like a device on the network, right? If you're sure it's not going to get knocked over from a port scan, run Nmap against it. Start trying to enumerate those network services and see if you have any vectors in that way. Don't forget the basics. Just because we're doing all this fun, new, novel hardware stuff, all the stuff you already know still applies here. So that's the real importance of that early threat modeling and attack surface mapping. For Wi-Fi, if your computer doesn't have a Wi-Fi card, there are some great external adapters you can get. It's also sometimes nice to have Raspberry Pis around for spinning up additional access points and messing with that kind of stuff on the fly. Bluetooth Low Energy is incredibly common, incredibly ubiquitous, and incredibly annoying. It is super pesky to deal with, and if anyone in here has come to the IoT playground, I'm sure it was a 50-50 chance of if our Bluetooth lab was working when you were there. Just with how noisy and crowded the 2.4 gigahertz spectrum is here at the event, and everybody running around with their flippers doing the Apple BLE spam, it is certainly interesting to deal with. Bluetooth can be very scary when you start looking at the protocol. It's a lot of weird acronyms, and it's not super intuitive when you're getting started. But come stop by, we'll show you some of the basics, and it'll make a lot more sense very quickly. Essentially, the flow you're looking at goes from advertising. This is, say, when you're trying to pair like a new set of wireless earbuds. And you go to your Bluetooth and you start looking for it in the menu. That's all the devices that are in the area advertising. Then you can go through the connection and pairing process. And this is a great place to look for some vulnerabilities, depending on how secure the device needs to be. The devices will communicate with GAT, or attribute characteristics. So when you connect to a device, you can see what services it's advertising, and then underneath services, kind of hierarchical, are these characteristics. So you may be able to read or write to them. That may control actions or get you readouts. It's going to be very device specific. For legacy pairing versus LE secure pairing, the LE secure pairing is going to use elliptic curve Diffie-Hellman cryptography for this exchange. If you're using the secure pairing modes, right, you'll have encryption, man-in-the-middle protections. Some of the legacy pairing modes, like the just works pairing mode, set the temporary code or the temporary key to just zeros. So if you see something using just pairing, there's a really good chance you're going to be able to sniff those communications and see what's being communicated, or get in there and actively man or machine in the middle of the connection. So things we might be looking for. Does the advertising info leak any sensitive information? Do characteristics require authentication or encryption? Right, again, that's going to look at what pairing modes and take a look at what you're seeing when you're doing this enumeration. Are unauthorized connections rejected? If you connect and fail to pair, but the device doesn't boot your connection, it might not start advertising again, so you may be able to stop other people from connecting to the device just by having an open connection hanging. This may seem like a nuisance for a lot of products, but consider a BLE-enabled, maybe access control system, smart locks on an office building. What if you could, tie up all of the lock's connections and stop those from having a door be locked, or stop it from being unlocked in the event of an emergency, for example? So again, with the real-world kind of tangible consequences, a lot of this stuff can become critical very quickly based on the business impact. And again, trying to sniff traffic over the air or man-in-the-middle connections. On the left are just some Bluetooth dongles. If your computer doesn't have Bluetooth, you'll want to pick some of these up. Also, it helps to have two, so you can do the man-in-the-middle connections, one to connect to the machine that you're spoofing, or that you're trying to spoof, and one to connect to the victim device. In the middle, these are some tools for doing sniffing packets out of the air. The top is the Ubertooth. This one I know is discontinued. They're very hard to get your hands on, but if you can, they're pretty good tools. Below that is a Halong. I think it's about a similar price point. I haven't worked with one personally, but Joe Hopper over in the IoT Playground has, and he says it's worked pretty well with him. Also, there's the NRF Connect. You can get this on your phone right now, and that works very well for a lot of these cases. It's great for some easy enumeration and just checking it out before maybe you go in a little bit more depth. Some software tools you might be looking at: Beetlejuice and GATTacker. These are great for doing man-in-the-middle, replay attacks, things of that nature. HCI tool and GAT tool, these are going to be great for interacting with those Bluetooth devices. BetterCap has a whole suite for reconnaissance and enumeration with a little bit more user interface, so that's a great option for people. If you like to script things and have some automation, Bleak is a Python module for interacting with these devices, also very useful, and you can find a lot of people's contributions on GitHub, so bake those into your own code. The Ubertooth One software, of course, if you can get your hands on one. Crackle is a utility if you have captured kind of the whole pairing connection for an insecure pairing mode. You may be able to derive that key and decrypt a PCAP or packet capture file and start poking through that way. Also, if the device you're testing is connecting to an Android phone, say for like an Android companion app, Android, you can enable this Bluetooth snoop log, and you don't even have to sniff stuff out of the air. It'll just record all of those communications. So if you don't have to sniff it out of the air, save yourself the headache. Another wireless interface you'll run into is Zigbee. This is going to have different frequency ranges based on the location, but almost everything I've seen just uses one of these worldwide channels. So again, all on the 2.4 gigahertz range, along with much of Wi-Fi and Bluetooth and Zigbee, so it gets very crowded. I won't go too much into how Zigbee works, but devices have different roles. You can go read about that. There's some great talks out here about targeting Zigbee. Some things we might be looking for, a lot of these are with how the network is configured and how encryption is configured in the network. If any of these keys are sent in plain text, we may be able to authenticate and pose as some of these special devices or decrypt point-to-point messages between devices in the network. One of the important things to know about Zigbee is it works as a mesh network. So all of the devices might not be connecting to, say the internet themselves, but they'll connect to each other and they can pass around data until it gets to kind of a broker that may send that up to the cloud. And again, with all of these, jamming can also be a potential concern. But again, that's going to require proximity to the direct victim. And a lot of times what we're really worried about is attacks that we can find once that scale everywhere. But again, with some of these wireless communications, we do have to be in range. Killer Bee is a great framework of tools to start working with this. And when it comes to hardware, there's the API moat on the bottom and then the RZ Raven stick. These are great. And again, things you might want to look at as you start getting into Zigbee or find out that device you're trying to hack uses Zigbee for communications. Then NFC and RFID, I'm sure people might be more familiar with these if you have access cards for hotels, the challenge cards for the capture the con here. We see these all around. Again, they operate in a couple different modes here, but when it comes to tools you might use to interact with them, there's tools like the Proxmark. This is very ubiquitous, and of course, the infamous Flipper Zero. Plenty of cool talks and demos online about this, yeah, really fun to look into. If the implementation is using a known insecure or vulnerable protocol, or is relying only on the UID for authentication decisions, those may be cases where a device is vulnerable, and you might want to check that out. SDR and miscellaneous, I didn't want to do SDR the disservice of trying to summarize it all in one slide. It is such a cool, dynamic field where you can get into so much depth. Some tools you'll use here, the HackRF1, the Yardstick, and an RTL SDR. We can demo that at the playground if anyone's interested, and that's got some software supporting on the back end. But I understand there were some CTF challenges here relating to radio, so maybe some of you encountered that and already did some learning here. But yeah, great talks out there. This is a really cool rabbit hole to dive into. Next up, we have some of the active testing for the firmware analysis. So as I've been saying, we don't want to just zero in on hardware and stay there the whole time. A lot of times the goal of our hardware hacking is to get us access to the firmware. Sometimes we don't even have to do that. Sometimes the manufacturers will have it online where you can just go download their firmware update. This may or may not be encrypted, and the devices may or may not validate a signature or that it's a trusted update. So that's definitely something to look for. You may be also able to sniff a firmware update. Say if it's getting a firmware update from the cloud over HTTP instead of HTTPS, you may be able to get it that way from sniffing it, or maybe from a mobile app. Maybe it gets the firmware update through the iOS companion app, and you can get it from reverse engineering some elements of the iOS app. Otherwise, you can dump the memory off of the device in a lot of cases if it's stored in memory that's either external and accessible or internal and they have debug privileges enabled. As I mentioned, sometimes you'll have to take it out of the circuit, but as we showed earlier with those special clips and the micro grabbers, sometimes you can do this in circuit. Also, if it has a bootloader like U-Boot, sometimes you can just ask it to provide some of the regions from memory, and it may be able to spit everything out for you. Once you have a firmware image, like we said earlier, you can use binwalk to try to figure out what's in it, but you can also go into firmware emulation. So you can use QEMU, some people call it QEMU, lots of fun names for it. You can also do full firmware emulation with the firmware analysis toolkit. This will have some problems for anything that has to shell out to hardware functions. Obviously, if you're doing this totally virtualized, it won't have those to call on. But if you got, say, a router's firmware package, you may be able to, emulate this router firmware and connect to the web portal that it's hosting and start trying to find, command injection or other normal web app vulnerabilities without even having one of these routers to test. So that's why I have the little asterisks on the maybe without access to the physical device. It depends on what features you're interested in looking at. We already talked a bit about binwalk, but this is going to be your best friend again when you have binary data for which you don't already know the structure. Some juicy targets we might be looking for in the firmware, any hard-coded secrets or certificates that we may be able to use against other devices or endpoints, any update mechanisms, especially over-the-air update mechanisms. And then again, a ton of your normal security findings, authentication and authorization controls, input validation. If we target application or product-specific binaries, that'll help us focus on things that are relevant to the context of the application. And again, check out what bootloader they're using and if there's any capabilities that can afford you. For binary exploitation on these devices, a lot of your normal binary exploitation skills should transfer over quite directly. But one thing you have to keep an eye out for is you might be working with different architectures than you're used to. So you may be used to, x86 and ARM and have never seen MIPS before. So as soon as you see, MIPS, there's a little bit of stuff to learn. But again, those skills should transfer over. And one benefit for you is that IoT devices might be a lot less likely to employ some common protections. So if you've been trying to, develop an exploit that bypasses ASLR, or you have to deal with stack canaries or no execute bits, a lot of times these lower power or cheap or rushed devices won't have those enabled. So you may have some luck with exploits there. When it comes to cloud testing, this is also going to be very interesting and kind of vary greatly based on the scope you're afforded. So if you're working with a client and they're willing to let you into their AWS or GCP environments, you may be able to do a much more thorough posture review. If this is something you're testing kind of as personal research, you may be much more limited in what you can check, at least on the infrastructure side. But one thing you can definitely look at is the communications to and from the cloud. You're going to see a lot HTTPS and then MQTT. MQTT is a publish-subscribe protocol, so lots of different devices can all subscribe to a topic, and then as new data is pushed to that topic, they'll all pull that down. So you can think about a potential case where an MQTT topic is used to deliver information about an over-the-air update. Well, if you're able to push to that topic without authorization, you may be able to get the whole fleet of devices that are subscribed to that topic to change their behavior and potentially expose them to some vulnerability. For those updates as well, if they're served over HTTP or it's not checking the signature, or you can provide old firmware with known vulnerabilities, right? You may be able to, tamper with those firmware images in flight, or again, download it to an image that has some known problems and try to exploit that. One difficulty here is, again, IoT devices making their way into, the medical industry. If you're in a hospital in a life-saving setting, they may be required to have these devices able to have their firmware downgraded. Because if a firmware update makes a machine stop working and it's essential for providing, critical life-saving care to someone, that's going to take precedence over reintroducing a security vulnerability. So there's a lot of trade-offs and kind of business use case and regulatory discussions that come into play here. It's a little bit of a different paradigm from some of the other areas in security. And then again, if we have access to that backend cloud infrastructure, if they maintain device-specific encryption keys, right, figuring out how those are stored, how those are accessed, is that infrastructure secure? Can we poison any updates? Really figuring what data is being sent back and forth. Again, this is going to vary wildly based on what devices you're looking at, but really great place to check. Wrapping it up here, just some additional resources. This is a listing of books that I found to be very helpful. A lot of these are from No Starch Press, really, really valuable. One I'm going to call out specifically, not a No Starch book, but this one on the top, the IoT Hacker's Handbook by Aditya Gupta. This is the same author as that Attify certification and training course I mentioned earlier. So with the book, obviously you don't get all of the hardware labs and exploitation, but I would say you probably get about 70% of the content, and it's only $30 for the book instead of, multiple thousands of dollars for the training. So if this is something you think you might be interested in, I'd highly recommend getting the book and working through the software-only labs. And, if you find a real passion fit for it, maybe that training could be right for you. I think the ACIP training does a really good job of covering the breadth of security, but with enough technical depth that you are really walking away from it capable of doing some of this work. And then these are just some of the YouTube channels and Twitter accounts, X accounts I've mentioned through the talk. These are some great resources. Go check out what they're posting, who they're reposting, and who they follow. There's so many great, personalities online that are willing to share all of their work. Can't fit them all into one slide, but I think I've mentioned all of these folks in here at least once. So that's all I've got. I know I'm a minute or two over here on time, so if you have any questions, please come by the IoT Playground. I'm happy to chat in as much detail as you want. We can get technical, we can keep it high level, beginner friendly, but I really appreciate you all taking the time to come out here and listen to me. Thank you.